Okay, I'm going to give you an overview of a survey that happened in the past, the Rosetta survey, and taking it to think about how we can pull in all the systems we were talking about yesterday into a big survey, and then how that fits into the concept of rings. So it's about integrated surveys. Sorry about that. And drawing in a lot of different investigations. And from that, you can see that this involved a lot of people and a lot of different institutions, a lot of discipline-specific collaborators. Is it hissing for you the same way it is for me? Oh, good. And we were working from the ice pod, which was operating with the Air National Guard's C-130s that are based at McMurdo. This is the ice pod, which you may well have seen. These are the instruments that sit inside. It hangs off the back of the cargo plane. It uses LiDAR and cameras to measure the ice surface. It uses a couple of different radars to measure the interior of the ice and the thickness. We're interested in the rock as well. I'm interested in the rock. So there's a magnetometer, and there was a whole pallet full of gravimeters inside this aircraft that was loaded every day on a forklift. And we also managed to hone that system down through the Rosetta surveys, so we ended up using really just this tiny little box here as part of the IceBridge surveys that overlapped with the Rosetta era, but this is that little gravimeter on the G5 in the last IceBridge season. And we were also investigating the ocean circulation under the ice shelf. So we had those Alamo floats. I don't know if I can make a video play here. Probably not. Okay. So you got to imagine that these guys are going to drop that box out of the back of the plane. If I did play the video, it would be horribly noisy, and that float would launch out the back and into the front of the ocean water in front of the ice shelf. Which I'll show you the points that it came in later. So you've got a whole suite. You can measure the ice, you can measure the ocean, you can measure the rock underneath it, all from this one platform. And this was the survey plan that we flew for Rosetta. There's details I'm going to point out later, but the important thing is going to be this line here, which isn't quite as straight as all of the others. And this is what we use to link the Rosetta survey in with the bigger IceBridge surveys. And that's where I think the really important thing for rings is going to be. But to just give you a sense of how much of an ice shelf you can measure from one integrated multi-instrument, multidisciplinary survey, this is a paper that came out just this year from Matt Tankersley, where he was using the magnetic data to map the basement topography, the hard rock under the sediments underneath the ice shelf, and found all sorts of things that speak to the tectonics of the development of the Ross embayment. Then this was my work, taking a layer up from that and using the gravity data to identify the bathymetry underneath the ice shelf. You can see that there's orders of magnitude of different relief on the basement and the topography, but they're not completely ignorant of each other, although they disagree with each other a lot. These are the points where we put the floats in, and we're able to measure the water properties in a series of dives. So this isn't just a one point, but it's a time series that I've just picked out a couple of points to capture the most important water masses that go under the Ross. Again, if I could play a video, this would turn into a numerical simulation of circulation underneath the Ross, because by combining these observations with ocean modelers, we were able to get an understanding of the melt processes that happen at the base of the ice shelf. And through those processes, we identified where processes are stable at the grounding line in the Ross, and the vulnerabilities for the Ross are at the front, there where that E is, where there's a lot of melting directly at the base of the ice shelf. That's seasonal flooding of warm water. But the figure that I show in the bottom there is from Indrani Das, where she was looking at the structure of the ice from the radar to try and tease out a decadal to centennial history of that basal melt by looking at the ice. So the ocean and the ice and the different scales of rock investigation all came together in this one gigantic project with a lot of different collaborators, and it's been able to go even deeper by this regional framework survey that we flew, being useful to target ground-based surveys that the New Zealanders have been pursuing over the last several years. So the different boxes there are places where there have been gravity and seismic and hot water drilling experiments based out of New Zealand. I got in touch and got a couple of slides about Discovery Deep, where they were exploring last season. And so this is a collaboration of a few New Zealand institutions who are doing ground-based work. And they're using historical ground-based gravity measurements. They're putting it in the framework of the Rosetta gravity grid and able to put in new surveys and seismic surveys that are targeting the sediment history of the Ross Ice Shelf area, so trying to find those deep sediments in the Discovery Deep. So this really has been a full spectrum inquiry that's worked on different scales and in different disciplines, and to my mind it shows how we can bring these processes together in these big surveys and look at it at all sorts of different scales. So to that, I step all the way back, and we're going to hear from Joe shortly, but these are the ice bridge lines that were flown that Lamont was involved in, with Rosetta tucked in there as well. It shows a pretty good coverage and a pretty good framework of lines around the ring edges that we've been talking about. If we just look at the Ross, I have the grounding line here, and then I have buffers that step inwards at 5 and 20 and 50 kilometers from the grounding line. You can see the difference that the bathymetry, the newly informed bathymetry makes. It opens up the water cavity so that we were able to understand that circulation. But you can also see that there's still a lot of work to be done. This is my purpose here. If you take each of those ice bridge lines, and we have about a 5 kilometer long track resolution of the gravity, so you imagine a 5 kilometer wide swath, and just work out how much coverage you have along one of those lines. In the Amundsen Sea, which we have flown to death, when we're right near the grounding line, we have about a 30% coverage. And as we come out to sea, that coverage diminishes in those lines, although it comes out to meet where ships have come in. Then in the Ross Ice Shelf, because it's a very different system, Rosetta flew, and we have less coverage at the grounding line. And as you come into the higher resolution parts of the survey, that's when we get up to close to the 30% coverage. So we've done a huge amount of flying here, but we still have a lot of coverage that we need to get if we want to get concentric rings to capture this system. Then the point that I alluded to earlier was these. You can see the Rosetta grid. You can also see all the ice bridge lines. And these two ice bridge lines were flown by the P3 out of McMurdo. They were aligned with Riggs ground base points, so we were taking ground surveys from the 1970s, hanging ice bridge lines on top of that, and then the Rosetta grid is bent along this line so that we can overfly it. And this is where I think that I should be wrapping up shortly, thanks. But this is where I think it's really important to make space for these big surveys that measure everything, and make handrails that we can plug them into to connect them with the rings that go all the way around the continent. And these also give really good opportunities to systematically overfly and reoccupy so that we can monitor for change, which speaks to what Duncan was asking about at the start. So this combined way of detailed surveys and a strong ring framework, I think, is what we're trying to head for, which is what I had to say there. So thank you.